Hi, in this video we are going to talk about the first graph traversal algorithm, the so-called breadth-first search. We usually refer to it as BFS. It stands for breadth-first search as well. Okay, so what is breadth-first search? What is it good for? For example, let's suppose that we have a graph and we want to visit every single node. Then we can do it with the help of breadth-first search. We are going to talk about depth-first search. It is the other famous graph traversal algorithm. So in breadth-first search, we visit every vertex exactly once. We visit the neighbors, then the neighbors of these new vertices, and so on. The running time complexity is linear in the sense that it's going to be ordo v plus e, where v denotes the number of vertices or nodes in the graph, and e denotes the number of edges in the graph. So because we visit every vertex exactly once, of course it's going to be linear as far as the number of vertices are concerned. The memory complexity is not that good because we have to store lots of references or pointers in a queue abstract data type. So that's why depth-first search or DFS is usually preferred. But it's very important that breadth-first search has several applications. For example, it yields a shortest path tree. So Dijkstra shortest path algorithm does basically a breadth-first search if all the edge weights are equal to 1. So we may come to the conclusion that okay, the memory complexity is not that good, but on the other hand, it has several applications, such as Dijkstra's algorithm or in artificial intelligence. So let's take a look at the concrete source code. It's very important that in breadth-first search we have to use a FIFO structure, a first-in, first-out structure, and that's why we use the queue abstract data type. So we have an empty queue at the beginning, and we keep checking whether we have visited the given nodes or not, and we keep iterating until the queue is not empty. So at the beginning we set the given vertex, the starting vertex, to be visited. We add it to the queue, and while this queue is not empty, first we dequeue, which means that we take out a single item, a single vertex from the queue. I named it as actual. Then we visit all the neighbors of this actual vertex. I denoted these neighbors with v, and if the v is not visited, then we set visited, and we enqueue it, which means that we add it to the queue. So that's why we are going to iterate as long as the queue is not empty. Let's see a concrete illustration. We have a tree-like structure with A, B, C, D, E, F, G, and H nodes or vertices. At the beginning, the queue is empty. If you recall the source code, first we are going to have the starting vertex and we add it to the queue. In this situation, the starting vertex is the vertex A, so we add it to the queue, and of course we set this node to be visited in order to avoid considering this node over and over again. Then we are going to dequeue the node A to be able to process it. What does it mean that we process it? That we visit all the neighbors of the vertex A. These neighbors are the B, so we add it to the queue. Then another neighbor of A is the node F, we add it to the queue. And the last neighbor is the G. It's very important that sometimes we call it neighbors, sometimes we call it children. If we are dealing with a tree-like structure, we usually call the neighbors children. So in this situation, the queue contains 3 items, the node G, the node F, and the node B. And we keep enqueuing. What does it mean? Queue is a FIFO structure. So the first item we have inserted will be the first one we take out. And the B was the first one, so we are going to take out the B. We dequeue it and visit all its children and put these children into the queue if necessary. What does it mean if necessary? If we haven't visited it so far. So we are going to consider B. Then we are going to consider its children or its neighbors, the C and the D, and of course we add it to the queue. Then we are going to dequeue or remove the next item from the queue. It's going to be the F, so we visit it. We come to the conclusion that F is a leaf node, which means that it doesn't have any children, so we are going to take out or dequeue the next item from the queue. It is the G. As you can see, the size of the queue is always changing. In this case, it keeps decreasing. The G has a single left child, the H, so we visit it and add it to the queue, and we take out the next item from the queue, which is the C. Of course, we remove it and consider all of its children. It is a leaf node, so we are done. We keep considering the next item from the queue, which is the D. We set it to visited, and we consider its children. It has a single left child, the E, so we add it to the queue, and we take out the next item from the queue, which is the H. Okay, we visit it, we come to the conclusion that it doesn't have any children, so we take out the next item from the queue, it's E, and we visit it. We come to the conclusion that there is no more item in the queue, which means that it is empty, which means that we have finished. We have been considering the pseudocode, and we come to the conclusion that we have to iterate while the queue is not empty. In this situation, the queue is empty, so we are going to return from the breadth-first search method, which means that we have successfully managed to visit all the vertices in the graph. And basically, this is exactly what we were looking for. Okay, so just to summarize it, breadth-first search is going to visit every vertex on a row-by-row basis. So we visit the A, then we are going to visit the next layer, the B, the F, and the G. Then the next layer, the C, D, and the H. Then the next layer again, the E, and so on. So unlike depth-first search, breadth-first search is going to visit every single vertex on a row-by-row basis. It's going to consider the items, the vertices in the local environment, and then it's going to go further. Depth-first search is a bit different. It's going to visit every node as far as possible without visiting the nearest one, for example. So that's the main difference between depth-first search and breadth-first search, but in the coming videos we are going to talk about depth-first search as well. So what are the applications? There are several applications for breadth-first search. For example, in artificial intelligence and machine learning, it can prove to be very important because, for example, robots can discover the surrounding more easily with breadth-first search than depth-first search. And basically, I have mentioned that breadth-first search is going to visit the vertices on a line-by-line basis, which means that it's going to visit the local environment, the local neighborhood first, before it's going to visit further vertices. For depth-first search, it is not true. And it's also important in maximum flow algorithms. For example, the Edmonds-Karp algorithm relies heavily on breadth-first search for finding augmenting path. Or garbage collection, for example, in Java Virtual Machine, this is the so-called Cheyenne algorithm. It helps to maintain active references on the heap memory. It uses breadth-first search to detect all the references on the heap that are active and is going to get rid of all the other references, also called as dead references. Or for example, serialization or deserialization of a tree-like structure. For example, when order does matter, then it allows the tree to be reconstructed in an efficient manner. So okay, we come to the conclusion that breadth-first search is not so memory friendly, but sometimes there are problems that can be solved very efficiently with the help of breadth-first search, unlike the fact that okay, it's not so memory friendly, we have to store a lot of pointers and references in the queue abstract data type, but whatever. So this is the breadth-first search algorithm. Thanks for watching.